Hello and welcome to my channel, to this new video on Spark Core, on our journey to understand how Spark executes workload on our cluster. And in the last video we talked about MapReduce and how it allows us to distribute workload on a cluster on multiple machines. And today we are talking about the API that Spark introduces to implement this idea, which is the Spark Core API. And the most important data structure we have there, or the most important abstraction they define, are RDDs, which stands for Resilient Distributed Datasets. And they are basically the core of the entire Spark framework. And today we're going to look in what's the abstraction that RDDs define to make our workloads even faster than MapReduce, and how they work internally. So that's a very important building block of understanding how Spark works. So let's dive right in. Let's get started. So as I said, the Spark Core API defines an abstraction over the MapReduce idea, which is the RDDs, Resilient Distributed Datasets, while the terminology datasets is slightly misleading because the RDDs are more a abstract computational procedure as they do not contain actual data. So the RDDs basically live only in the driver and constitute a computation procedure which we define in our user program by applying transformations and all the code you write in the Spark Core program. And they end up being only a procedure which describes how a result can be executed and produced by the cluster. So here I listed the 6 traits the authors also state in the paper. So on RDDs we define coarse-grained transformations, which means they provide a declarative API. So we use these coarse-grained transformations to tell the framework what we would like to, or in what manner we would like to transform our data, and not step-by-step imperative procedures. Then they are partitioned, which is directly related to MapReduce. So we use data decomposition to actually parallelize workload on our cluster. They are immutable. So when we transform one RDD into another by applying one of these transformations, we actually get a new RDD. So the RDD doesn't get changed. We always get a new derived RDD if we apply a transformation. Then they track the lineage, which means it is always recomprehensible what happened to an RDD and how it is derived from a parent RDD. And by having multiple transformations applied to our input data, we also get a whole line of transformations. So we are always able to reconstruct our result from the input data simply by applying or reapplying the transformations again on the input data. Then they are lazily executed, which leads to the fact that they are more an abstract computation procedure rather than holding data, because the lineage allows us to recompute our result from any step in the chain of transformations, and they are not evaluated until we perform an action. And we're going to see what the difference between a transformation and an action is. But for now, it's important that our RDD is only evaluated on our cluster once we call an action. So an action is always that point in the transformation chain where we want to see the result. And finally, they are persistable, meaning we can cache them or write them to disk. All right, so the interface we see in Spark Core code looks basically like this, and these 5 traits and methods on RDDs are the essential building blocks which are used for all scheduling and execution on the cluster. And it's very simple. So an RDD basically has a type. So that's basically the type of objects it contains. And then, as I said before, it's partitioned. So it has a list of partitions that belong to that RDD. Then it has a set of dependencies, which is basically the parents, which it is derived from. And then we have an iterator, which allows us to iterate over the records of one single partition. And we basically pass around this iterator all the time because we have this lazy evaluation. So we don't actually have records in here, but we pass around an iterator so that we can work on all the records in a partition. And then it also holds metadata about preferred locations. So this data is populated as we transform our RDD. For example, if we have a file load RDD, which is partitioned among our cluster, we would hold preferred locations of the files of the workers where the files reside. So our framework can actually optimize and schedule tasks on the workers where the input files reside or where they are stored currently. That also holds for map output files, as we saw in the MapReduce. If there is a map output file already on one worker, it would make sense to schedule subsequent tasks on that worker as well. And then finally, we have a partitioner, which is basically the function which specifies the partitioning of this single RDD. All right, now let's look at what happens if we apply a transformation to an RDD. So at first we have RDD1, which is the result of a parallelize, which basically takes a list of values or records and partitions them, and we want to create an RDD out of a list of records. So we end up with an RDD1 of type T, and it's already partitioned. So in this example here, we have 3 partitions, and then on that RDD we call the coarse-grained transformation, and we want to map each of the values to a different value, and that's depicted by this function here. So we apply the map function and we transform type T to type U, and that could be any kind of thing. But as we learned previously, the map function always acts on only a single record. Now what we get is a new RDD, which is RDD2, because RDDs are immutable, so we basically duplicate it. And the new RDD also has partitions, and as we are dealing with a map function, we would basically have the same partitioning as the input RDD. And what we can also see is that the child RDD, in our case RDD2, has a dependency to its parent. And if we look at a more complex example like this one, where we have basically we start with 2 RDDs, RDD1 and RDD3, and both are created from a list of records. And then we apply transformations, for example, our map transformation here. It's the same picture than on the slide before. And on the right side, we basically have a filter, which is also dealing on individual records of the RDD. We get a new child RDD, RDD4, which is of the same type, and it also references its parent here. And then we want to join these two by applying the join coarse-grained transformation. And we end up with a new RDD, RDD5, which is a combination of U's and V's. And this RDD has basically a dependency to both of its parents. And what we can see if we focus only on the RDDs here is that we basically, from the RDDs and their dependencies, basically the pointing to their parents, we see that we are creating a graph. And this graph is directed because the edges from the child RDD are directed to the parent RDDs. And it's acyclic because even if we did the transformation back here from this map, we wouldn't end up with RDD1 again. So they wouldn't create a cyclic dependency, but rather we would get a new RDD, RDD6, which is again a child of RDD2. So our graph has to be acyclic, because otherwise we would have cyclic dependencies which we cannot resolve in our execution. Now, as we look at this acyclic graph here, the question we can ask is, why should we define such coarse-grained transformations and do all the hassle with a directed acyclic graph? And the point is, we are defining those coarse-grained transformations here, and our Spark framework, it knows their semantic meaning. For example, a map has a semantic meaning of only acting on one record, and the filter, we also know we can make the decision for each record individually. But for a join, for example, we know that we have to group data together which have the same key. And now we can use this information about the intention of the programmer, what he would like to do, to schedule this workload most efficiently on our cluster. And most efficiently means we would like to avoid transferring data over the network, and also serializing and deserializing data for the transfer. So Spark implements all of that only to be able to optimize how this exact computation procedure or abstract computation procedure can be most efficiently computed on our cluster. In order to do this optimizations that I talked about before, Spark uses another abstraction within its framework. And on top of the transformations that we saw, Spark assigns internal dependency labels. And there are basically two types of dependency that there can exist. The first one is the narrow dependency. That's basically when the child partition is dependent on at most one parent partition. So having this criteria allows us to infer that all the records that we need for our transformations are already in the right partition. So we can take any of these records, any of the records in this red partition, and one by one apply our function, and we end up with a new partition, which is the result of the transformation. And we don't have to put records into different partitions, so there's no shuffle involved here. On the right side, we can see the Y dependency, and that's defined when a record in the child partition has one or more dependencies to other partitions in the parent. So for example, if we have a join, we want all the records with a specific key to end up in one child partition. So the records with the value of the key we're looking for could be distributed here among all the partitions. And now we need to shuffle our data into one partition so that we can apply our aggregation on all of the keys of all of the records for one specific key. And we can see that our group by key, reduce by key, join, sort, they are wide dependencies because they take into account a key and eventually need or require the shuffling of data. Now we could ask, why do we not have narrow transformations and wide transformations, but rather we have narrow dependencies and wide dependencies? And the thing is, the group by key transformation, for example, is not intrinsically a wide transformation. And that's because this RDD, for example, here, 1, it could have potentially the exactly right or the exact right partitioning such that we can apply the group by key transformation without involving any shuffling. So if this RDD is already grouped by the right key, we would basically end up with a narrow transformation, a narrow dependency, even though we have a group by key and then an aggregation. So that's a very important distinction at this point. All right, having understood that in our user program, we are basically defining a chain of transformations by using coarse-grained transformations which have semantic meaning for our framework. and we end up with a transformation lineage and a abstract computational procedure that we are creating in the Spark framework by using their RDDs. Now we have this directed acyclic graph, which specifies dependencies and partitions for each of our RDDs. And now we can talk about the most important optimization that Spark can do for us using the RDDs in the core API. Now that we have our abstract computational procedure with dependencies, wide and narrow dependencies defined between the RDDs, Spark can go ahead and say, okay, we have one dependency here, and we can already tell it's a narrow dependency. So each of the RDDs execution function acts on the on a single record, and we don't need a shuffle in between. So what Spark does for us is something called pipelining, and it looks at the directed acyclic graph and checks for narrow dependencies. And there could be any transformation, as I explained before. This could be a group by as well, but still we would end up with a narrow dependency. So whenever we have a narrow dependency, we already know that there is no need for a data shuffle. So we don't need to move data from various partitions into one. And therefore, we don't have to schedule these two evaluation functions one by one, but we can actually combine them or consolidate them into one execution acting on the records. So pipelining means that Spark consolidates narrow transformations or the evaluation of narrow transformations and schedules them as one task on our cluster. And that's what we call a stage in the end. And we're going to look at this in the next videos. But the same happens on this side. So here we have a narrow dependency in between again. So we can basically schedule these two evaluations simultaneously or in the same execution on our cluster. And by doing so, we are reducing a lot of overhead which we had in the MapReduce, or if we didn't pipeline, because every shuffle or data exchange between workers involves a serialization, a transfer of data, a synchronization between tasks, and then also a deserialization of data and then serialization again. So we're saving a lot of effort, and that's the most expensive effort when we parallelize workload on a cluster. Okay, one final remark about what's happening within Spark Core. If we apply a transformation which can be labeled as a narrow dependency to derive the child RDD. So on the top here we have RDD1, which is the parent RDD, and then we apply the narrow transformation, which acts on a single record, so we know it's a narrow dependency between the two. And then what happens is the partitions are taken one by one to the child RDD, because we have a narrow dependency and we don't need any shuffling. Then the dependencies of this RDD2 is simply one dependency to its parent. So here we introduce a reference to its parent RDD. We can also preserve the partitioning. That's why we take over the partitioner from the parent RDD, and the preferred locations would also remain the same. And as an iterator, we simply use the iterator to the output of the parent RDD. And that's pretty straightforward. And all of these decisions can be made based on the transformation the user uses in the program and the information which is already present in the parent RDD. And that's basically what the Spark Core RDD API implements. It implements these transformations that we are handed out using the API, and then it implements the behavior, how each of the transformations transforms the parent RDD into a child RDD. I think it's very powerful, especially the pipelining, and we are modeling dependency types based on the information we have about the RDDs and the transformations. And using these dependency types, we can optimize the scheduling. So we can schedule the RDDs, which are related by a narrow dependency in one execution step on our cluster. I hope you found this video interesting and you could take away something, some understanding how Spark Core works. We are going to continue our journey and see how high-level APIs like SQL build up on top of that to provide even more optimizations that the framework can do for us. In the next video, we will look at the Spark execution model, what's a shuffle map stage, what's a result stage, and so on, so that we can interpret the metrics we're seeing much easier. And all of the things I mentioned before, or right now, are part of Spark Core, not Spark SQL. So there you can already relate that all of the Spark SQL workload is actually transferred down into the RDD API and then executed on the cluster. So what we have just seen is actually right the core of any Spark application. All right, if you like this video, please leave a like, or if you have some comments, leave them down below. Make sure to subscribe this channel if you would like to stay updated. And yeah, thanks for tuning in. Until next time, see you then. Bye bye.